Good morning, doctor. I'm Chong Yi Ling. So I'll be presenting on 13.3 partial derivative. So let us look at the definition for the partial derivatives of a function of two variables. So the partial derivative of fxy with respect to x at the point x0, y0 is delta f delta x equal to limit h approaching 0, fx0 plus h, y0 minus fx0 y0 over h, provided the limit exists. A variety of notation are used to denote the partial derivative at the point x0, y0, including delta f delta x x0, y0, fx x0, y0, and also delta z delta x x0 y0. The partial derivative of fxy with respect to y at the point x0 y0 is equal to delta f delta y equal to d dy fx0 y equal to limit h approaching 0 fx0 y0 plus h minus fx0 y0 over h, provided the limit exists. So the partial derivative with respect to y is denoted the same way as the partial derivative with respect to x. So delta f or delta y x0 y0, fy x0 y0, delta f or delta y, and fy. So let us look at some example for the calculations part. So the question given us to find the value of delta f delta x and delta f delta y at the point 4, -5 if fxy is equal to x squared plus 3xy plus y minus 1. So to find delta f delta x, we need to treat y as a constant and differentiate with respect to x. So delta f delta x is equal to, we differentiate this equation with respect to x. So y, we treat it as constant, so we get 2x plus 3y plus 0 minus 0, and you get 2x plus 3y. So you substitute 4 and -5 into this equation, then you will get -7. So to find delta f delta y, we treat x as a constant and differentiate with respect to y. So we differentiate this equation with respect to y, so we will get 3x plus 1. So the value is substitute 4 and -5 into this equation, then you will get 13. So just now we have looked to the function with only two variables. Now we will look to function with more than two variables. So it's actually like the definition for function with two variables. They are ordinary derivative with respect to one variable taken while the other independent variables are held constant. So for example, if x, y, and z are independent variables and fxyz is equal to x sine y plus 3z. So in this case, we want to find delta f or delta z. So we need to differentiate x sine y plus 3z with respect to z. So we treat x and y as constant. So we treat x as constant first, then we differentiate sine y plus 3z with respect to z. So we use the chain rule and we will get this equation. So we treat y as the constant, then we will get 3x cos y plus 3z. So for second order partial derivative, so when we differentiate a function fxy twice, so we will produce its second order derivative. So these derivatives are usually denoted by delta square f delta x squared or fxx, delta square f delta y squared or fyy, delta square f delta x delta y or fyx, and delta square f delta y delta x or fxy. So defining equations are delta square f or delta x squared equal to delta delta x bracket delta f delta x, delta square f delta x delta y is equal to delta delta x delta bracket delta f delta y. So notice the order in which the mixed partial derivative are taken as below. So delta square f delta x delta y. So we need to differentiate with respect to y first, then only with respect to x. So for fyx is also similar with this. So we need to differentiate with respect to y, then only with respect to x. So let us look at another example. So fxy is equal to x sine x squared y. So the first step is similar. You need to calculate for both first partial derivative first. Then you in this equation, so you calculate the delta f delta x, you will get this equation. Then you find the delta f delta y, so you differentiate this equation with respect to y and treat x as a constant, then you will get this equation. So now, by obtaining this first partial derivative, we can use them to find the partial derivative of each first partial. So for delta square f delta y delta x, so you use this equation, delta f delta x equation, and you differentiate it with respect to y, then you will get negative 2x for y sine x squared y plus 3x squared cos bracket x squared y. So another delta square f delta x delta y is similar, so you need to find delta f delta y first, then you use this equation and you differentiate it with respect to x. Then for this equation of delta square f delta x square, so you find the delta f delta x first, which is this equation, then you differentiate with respect to x, then you will get this equation. Then for delta square f delta y square, so you differentiate it with respect to y, so you will get this equation. Then you differentiate this equation with respect to y again, and you will get this answer. So for theorem 2, mixed derivative theorem. So let us look at the definition for mixed derivative theorem. So if fxy and its partial derivative fx, fy, fxy, and fyx are defined throughout an open region containing a point AB and all are all continuous at AB, then fxy AB is equal to fyx AB. So let us look at the example for the mixed derivative theorem. So if x, y, and z are independent variables and w is equal to ln 2x plus 3y, so find delta square w over delta x delta y. So delta square w over delta x delta y. So first thing we need to differentiate delta w delta y. So we differentiate this with respect to y, so we get 3 over 2x plus 3y. Then we differentiate it with respect to x, so we get negative 6 over 2x plus 3y squared. So according to mixed derivative theorem, wyx is equal to wxy. So let us verify it. So we find delta square w over delta y delta x. So we need to differentiate with the respect to x first. So we get 2 over 2x plus 3y. Then we differentiate this equation with respect to y. So we get negative 6 over 2x plus 3y squared. So now let us look at the definition for the differentiability. So a function z is equal to fxy is differentiable at x0, y0 if x, x0, y0 and fy, x0, y0 exists, and delta z is equal to fx0 plus delta x, y0 plus delta y, minus fx0, y0 satisfy an equation of the form delta z equal to fx, x0, y0 delta x plus fy x0 y0 delta y plus epsilon 1 delta x plus epsilon 2 delta y, in which each of epsilon 1, epsilon 2 approaching 0 as both delta x delta y approaching 0. We call f differentiable if it is differentiable at every point in its domain and say that its graph is a smooth surface like this. So now let us look at the theorem 3, which is the increment theorem for function of two variables. So suppose that the first partial derivative of fxy are defined throughout an open region R containing the point x0, y0, and that fx and xy are continuous at x0, y0, then the change delta z is equal to fx0 plus delta x, y0 plus delta y minus fx0, y0. In the value of f that results that from moving from x0, y0 to another point x0 plus x, delta x, y0 plus delta y in R satisfy an equation of the form delta z equal to fx, x0, y0, delta x plus fy, x0, y0, delta y plus epsilon 1 delta x plus delta epsilon 2 delta y, in which each of epsilon 1, epsilon 2 approaching 0 as both delta x, delta y approaching 0. So corollary of theorem 3, if the partial derivatives fx and fy of a function fxy are continuous throughout an open region R, then f is differentiable at every point of R. So if z is equal to fxy is differentiable, then the definition of differentiability ensures that delta z is equal to fx0 plus delta x, y0 plus delta y, minus fx0, y0 approaches 0 as f delta x and delta y approach 0. So this tells us that a function of two variables is continuous at every point where it is differentiable. So the last theorem is theorem 4, differentiability implies continuity. So for theorem 4, differentiability implies continuity stated that if a function f(x,y) is differentiable at x0, y0, then f is continuous at x0, y0. So from corollary 3 and theorem 4, a function f(x,y) must be continuous at a point x0, y0 if fx and fy are continuous throughout an open region containing x0, y0. So that's all from me. Thank you.